What about 7 and 8? They don't look exactly like polynomials or rational functions or square root functions or constants, right? They look a little different. These are piecewise defined functions. So piecewise defined functions, the way that we figure out where these things are continuous is the following. First, we look individually at each one of the equations in here and figure out where are they continuous. Well, x plus 5 is polynomial. It should be continuous everywhere. 2 is a constant. It's continuous everywhere. Negative x squared plus 5 is a polynomial. It's continuous everywhere. So we first look individually at each one of those equations. After we do that, then we have to determine, hey, are we continuous at the point where we're changing? And where is that point? Well, we are changing at x equals 0. So when you're given piecewise defined functions, first you look at each one of those equations, make sure everything's good with continuity there, and then you're going to figure out, well, am I continuous at the place where my equations change? And in this case, am I continuous at x equals 0? Well, how do I determine that? Remember, there are 3 things needed for continuity. The very first one is that we have to be defined. So is f of c defined? Well, I don't know. What is f of 0? Can I find f of 0? Well, if I'm trying to find f of 0, that belongs to my middle equation. F of 0 is equal to 2, so I'm defined. Perfect. The second one is that my limit exists. In order for my limit to exist, I need to find the limit from the left and the limit from the right in this case. So let's figure out what the limit as x approaches 0 from the left of this function is. Well, the limit from the left is numbers that are smaller than 0. So that's the top. So 0 plus 5 is equal to 5. What about the limit from the right? So the limit as x approaches 0 from the right of this function is going to end up being the bottom equation, because that's where numbers are to the right of 0. So I'm looking at negative 0 squared plus 5. Well, that's also equal to 5. So since the limit from the left and the limit from the right are the same, we can say that the limit as x approaches 0 of this function is equal to 5. So condition number 2 is met. Condition number 3 is saying that the limit as x approaches 0 of f of x has to equal f of 0. Is that true? Does 5 equal 2? No. Therefore, we are not continuous at x equals 0. We're not continuous at x equals 0. So we could leave it like that. We could leave it as negative infinity comma 0 union 0 to infinity. Those are places we are continuous. Okay, so when you have a piecewise defined function, you're going to have to check and see whether you're continuous at that point. Now, in some of the problems, it wants us to graph these. So what I'm going to do is I'm going to graph this piecewise defined function for us. And this is something that hopefully you've seen before in an algebra class. I'm going to graph it. I'm just going to squeeze it in right here. So the first thing I'm going to do is I'm going to graph the top equation. Well, my top equation is x plus 5, and that only exists to the left of 0. Well, that's a line. It's got a y-intercept at 5. I know that's an open circle because it's not included. And a slope of 1 over 1. So I'm going to go down 1 and 1 to the left. So that's the graph of x plus 5 if x is less than 0. The middle equation is just a dot because it's the number 2 if x is equal to 0. Close circle here. And the last one, or the bottom equation, is negative x squared plus 5. And that only exists where x's are greater than 0 or to the right of 0. Well, that is a quadratic that opens down because it's got a negative leading coefficient. So it's up at 5 and it goes down. Make it look like a quadratic. So that is the graph of that piecewise defined function. On an exam, I would not make you graph a piecewise defined function. Let's look at number 8. Same thing, discuss the continuity of this thing. Well, I start by looking at each individual equation. What's the continuity at x? Well, x is a polynomial, continuous everywhere. 2x minus 1, also a polynomial, continuous everywhere. So I need to figure out, hey, am I continuous at x equal 1? I don't know. The first thing I need to do is figure out what f of 1 is. Well, f of 1, that exists for my top equation because that's where I'm equal to 1. F of 1 is equal to 1. So I am defined. The second thing I need to do is figure out what the limit as x approaches 1 from the left is of this function, and then as x approaches 1 from the right. Well, 1 from the left is, again, that top equation because those are numbers that are smaller than 1. Well, f of 1 for the top equation would equal 1. What's the limit as x approaches 1 from the right of this function? Well, that's going to be the bottom equation because those are numbers that are bigger than 1. So plug in, we get 2 times 1 minus 1, or 1. So the limit from the left is equal to 1. The limit from the right is equal to 1. Therefore, we can say that the limit as x approaches 1 of f of x is equal to 1. In order for this to be continuous at 1, the limit as x approaches 1 of f of x has to equal f of 1. Is that true? Well, the limit as x approaches 1 of f of x is equal to 1, and then f of 1 is equal to 1. Therefore, we are continuous at that point. And that means we are continuous everywhere, or negative infinity to positive infinity. Again, if we want to graph this, and again, you'll have to graph it, I think, in some of the problems. At 1, I was at 1, and that gets a closed circle. Well, this is a line again. X is just a line, and it's got a slope of 1, so down 1 over 1. And then 2x minus 1 is also a line. So this is 1, 1, and it's got a slope of 2, so up 2 over 1. There we go. That is the graph of that piecewise defined function.